We're good. All right, what do we do? Where are you going?
Nowhere. Bring some good news.
You want me to help you?
No.
Get you a glass and stuff. Hold on, let's never, hold on. Oh, shit.
Where's he going?
Yeah. You want a cup?
No,
No?
I didn't bring it right with me.
Okay, all right, good, you know where it is. He's taking a liking to prune juice. I guess that's an old person thing, I don't know. But it's a thing now, so. There you go. There we are.
Mr. Bert come on a flight last time.
He did this time too. Even though I was in Virginia, he didn't ride back with us. It was just mom and I that went and came back together. He flew in yesterday. I picked him up yesterday and he'll fly out on Sunday afternoon. So it's real nice
It's
because
short.
it's 6 days. Plenty. 6 days is plenty. But they'll get in a wheelchair so he doesn't have to walk very far, and they'll put him in the wheelchair and they'll take him all the way to his seat on the plane, and then they'll bring him all the way out to me. It's great. They do a good job. He always makes friends with the wheelchair people. Your suspenders twisted. Oh, they're back.
Hmm.
There you go.
Thank you.
Yes, sir.
Lesson 12.
Yep. Last week was 11. Did y'all do okay with your video lesson?
Yeah, but it was pretty hard balancing the equation.
Yeah, we're gonna practice more today.
It's very, very confusing. I searched on YouTube balancing equations. Like the element that balancing that thing was after you knew how to balance them out.
Yeah, it's
It's a little tough.
were you looking at net ionic equations or just regular chemical equations?
Regular.
Yeah, we'll practice it a lot. And there will
My
be
brother had
some,
to do his like stuff, and then he's like slash ionic, and then he and then he read it, and it was like 2 by 4 blah 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 blah.
yeah,
All
the
this
ionic
stuff.
is a little harder, but when you practice just balancing chemical equations, it gets a little easier.
I think next week we're gonna do the balance of chemical equations, stoichiometry.
Yes, next week we do stoichiometry. I think you're right. Yep. So we'll keep practicing, and there will be some like on your exams.
We have to turn in lab 12.
Next week? No, this week? Yes, this week you will have to hand in lab 12. Everybody will hand in a copy. But it's not too hard. Everybody should be able to do it. So everybody will hand in a copy.
What's the date today?
Today is the 5th
of November, the election day.
I was gonna say, how could you forget? I saw a funny photo of a guy. It was a man with sunglasses on, and he had like a cigarette, and he was looking like 70s cool, and he's smoking the cigarette, and it said, "Me watching the 2024 finale," and I'm like, that's about right. That's how I feel today. Let's just get it. Then we'll be done, hopefully very soon. I hope this doesn't dry out because I just want it over. It looks so pretty outside with the leaves. Like, I'm loving the fall weather. It's finally cool. Took
My
long
mom's
enough.
like, really want summer.
No, summer. What's wrong with her? No, tell her she's crazy. We need a nice fall and a good winter.
Oh,
I'm excited for
I
cooler
love
weather.
winter.
I need the cooler
My
weather.
favorite season's winter.
Yeah?
I've never seen snow in Georgia except when I was sick in 2021.
Mhm. We get it. It's just it's not as common, but
Mild
we get it.
snow, very mild. It's just like snow happen. When and why does snow happen? Snow happens
Snow?
because
It's
like
cold.
it's basically like rain, but
It's rain when it's cold enough. Yep. And it comes down and then it catches with other little
I
flakes.
really love snow. I remember in
Yeah.
Ohio I used to play
I hope we get some this year, because I like 1 or 2 good snow days. I don't want it to snow every day. I don't want to deal with it all winter. But I want 1 or 2 days where they have to close school and there's snow on the ground, and I want it at least 3 inches, preferably more. The first year we lived in this house, it was so amazing. We had
2000.
it was 2017 when we moved in here. No. Yeah, I think, and it was the best snow we had, and I came down. I woke up really early one morning and it had snowed overnight, and I was excited, and it woke me up, and I looked and I saw it and I was like, oh, that's pretty. And I laid down right there on the couch and I passed out for like another hour or two. And when I woke up, the sun had come up and I was looking straight out that window, and it was just pouring down snow. And everything was white, and it was one of those like magical moments. I was like,
I mean,
hey.
Like their Essen lane, like my lane, there's like snow all over my car.
Oh, wow,
My
that's
lane.
so
I'm
cool.
like, when will that happen again?
Yeah, when will we get there? Hey, girl. You know, Annabelle's probably gonna have to sit over there with you, because she usually sits here. So here she comes. Hey, Annabelle, can you sit on this side today? Do you mind? So for those of you who just came in, it's my dad, Mr. Bernard. Daddy, this is Annabelle
okay,
and Emerson and Everly.
oh, that's great.
Yeah.
Y'all in here, Joe?
Let's do one before we
This guy
start.
talked to me, so I'm the smartest man in the world. I said, why is that? I know it's in every book, every library in the world. I said, really? You must be smart. What is it? He said, words.
Oh, boy. All right, does everybody get your stuff out so we can start? And did everybody do okay with their virtual lesson last week?
Yeah.
Sorry about the change of plans, but we needed to do it.
And I heard you guys brought donuts.
I do have donuts. I have Tinker Day donuts today. Everybody will get some Tinker Day donuts. Hooray, hooray. Excellent. So today we're going to talk about controlling chemical reactions. So we've talked about signs of reactions. How do you know a chemical reaction has occurred? Can anybody remember a sign? What's a sign?
Color change.
Color
production of
change.
Odor.
Yes.
Production of the heat.
What do you think?
Change of temperature.
Yeah,
Gas
change in temperature.
bubbles.
Yeah, gas, that's right.
Formation of the gas.
Anybody remember anyone? Any other ones? How about
Fireworks.
odor, electricity, sound? There you go. Very good. Those are all signs. Production of sound can be a sign. Not always, but it can be. You can produce sound other ways, obviously. But those are signs of chemical reactions. Now we're going to talk about how do you control the rate of a reaction? How fast or how slow a reaction happens? Sometimes we want reactions to happen faster, and sometimes we want them to be slow. So let's talk about that. All righty. So first things first, how do chemical reactions get started? What? There you go. That's what we're going for. All right. So it would be activation energy. What does it mean to activate?
It means to
Wait a minute. Annabelle, what's activate?
start.
To start something, right? So this is the energy that's needed to start. So it's the minimum amount of energy needed to start a reaction. Could you have more than the minimum of energy present? Could you? Yeah, but we only need a certain amount, and the minimum amount that you need is your activation energy. So all chemical reactions require a certain amount of activation energy to get started, and that amount is different for different reactions. Okay, so what affects the rate? Okay, so first off, we kind of got to understand what rate is. What is rate? A rate is a ratio. What's a ratio? You know what's a ratio?
Yep, it's like it's like kind of like a fraction. But
Yeah, it's kind of like a fraction. So right now in this room, we have 1, 2, 3, 4, 5 girls and 1, 2 boys. So our ratio of girls to boys is 5 to 2, and our ratio of boys to girls is 2 to 5. Very good. So
simplified ratios, like if there was, say, like there were like 10 girls and
Mhm.
5 boys, you can simplify it to
Yes,
1
you can
divide.
divide it, just like everybody knows how to reduce a fraction, right?
Yeah.
Like if I said 6/12, how would you reduce that? What would it become?
You did
6/12.
1 by 2.
Yeah,
One divide.
6/12 is equal to 1/2 because 6 goes into 12 2 times. 6 goes into 6 1 time, it goes into 12 2 times. So a ratio is kind of like a fraction, but it compares two quantities measured in different units. Now that's important. It's two quantities in different units. So in my example of boys to girls, our units are boys. And Lucy, what's our other unit? If we were doing boys to girls, one unit is boys, the other unit is girls. There you go. So you're comparing two units, all right? Often with respect to time. Now that's where rate matters. So a great example of rate that you're probably familiar with.
Distance
It's
equals
speed.
speed divided by time. No, I mean distance.
Speed equals-
Distance over time.
Yeah, distance over time. When you're out on the highway and you see that sign and it says 6.5 speed limit, what does that mean? What's the 6.5? Anybody know?
The speed limit is 65, which means you're supposed to drive around that number.
Around that number. Well, what's that number mean? 65 what? Do you guys know?
Speed limit.
Wait,
Miles
you're saying miles per hour. So your unit is miles and your next unit is hours.
And miles is the distance divided by per.
Time, which is your hours, right? So 65 miles per hour. So that's an example of a rate. All right, so now we understand what a rate is. Now we have a reaction rate. So in chemistry, the rate of a reaction is the speed at which the reactants are converted into products. In a chemical reaction, where do you find the reactants? On the right or on the left?
On the left.
On the left, good. On the left, and then what's on the right?
Products.
Products, good, Emerson. Yes, products. Okay, so it's calculated by dividing the change in concentration by time. Okay, what is concentration? So let's say I had 10 atoms of, oh, I don't know. What's
Let's
a
say
good
you
one?
have 5.
If I have 10 formula units of sodium chloride in water, and then a few minutes later, I only had 5 of them that remained sodium chloride. The others had disassociated into sodium and chloride ions. That's my concentration of sodium chloride has changed. Your concentration is how much of something in a given volume. So if I have 10 milliliters, right? That would be crazy. You couldn't measure 10
Like in a
formula.
box, there would be there's an insect that would be very less concentration in a box. There'd be like 1,000 insects that would
Mhm.
have bigger concentration.
That's a great example. So right now, the concentration of people in this room is greater than the concentration of people in the pub room because she has 3 people in there. And we have how many in here? 7, right? Okay. So what are some factors that affect our reaction rates? All right. Anybody know? What is something that affects the reaction rate? Do you know? Lucy, do you know anything? Emerson, Everly, a factor? What do you have, Annabelle?
Factor that can affect
You know?
rates of
Can you
reaction.
think? Look at your notes. It might be there. Do you know?
Concentration?
Concentration's 1.
I mean, and
Annabelle, did you find one?
catalyst.
Yeah? Annabelle?
Inhibitor.
Inhibitors and catalysts. Okay, so there's lots of things. All right, so surface area, temperature, concentration, and the presence of catalysts or inhibitors. All right, so let's talk about each of these things. Surface area. The surface area is, what does it do to the speed of the reaction? If you increase the surface area, what's going to happen to the speed of the reaction? Do you know? What do you think?
Increase.
Yes, it's going to increase it. So if you have more surface area, it's going to make the reaction happen faster. And if you decrease the surface area, then what's going to happen, Lucy? You decrease it, what's going to happen to the speed of the reaction? If you increase it and it increases the speed of the reaction, then if you decrease the surface area, it's going to what?
Decrease.
That's a girl. Decrease it. Very good. All right. So let's see some examples. Let's talk about it for a minute. Everybody see if you can come up with one. Let's see. Everly, Can you think of a real life example where surface area might affect reaction rate? Can you think of one? Everybody start thinking of one. Everly, you think? Lucy, you think? If you come up with one, raise your hand. What do we think? He's looking.
Maybe like instead of if you're like if you're like putting dye in water and like you put less dye, it's gonna affect it less.
Yeah, but that's not gonna be a chemical reaction, but that's a good thought. What do you think, Eunice?
It's like when a building gets fire.
Oh, that's a good example. Fire. Yeah, okay. Have you ever taken paper and put a whole sheet of paper in the fire and watch it just whoosh really fast? Just burns up super fast because there's a lot of surface area.
I've seen a famous photo where these people where these firemen are inspecting a fire and the fire is on the house and this girl closer to the camera is just smiling.
I've seen that. Yeah, it's kind of weird. All right, so here's some examples. Burning wood. That's what you just suggested, Eunice. So compare burning a large log to burning of small twigs. They're made of the same wood, but the twigs are going to burn faster because they have more surface area exposed to the oxygen needed for that combustion reaction. And that leads to a quicker reaction rate. Alka-Seltzer. Do you know what Alka-Seltzer tablets are? They're these little flat round tablets and you put them in water and they fizz. It's a medication that makes your stomach feel better when you're not feeling well. So they fizz slowly in water, but if you crush them into pieces, they're going to fizz even faster because now you've increased the surface area. Also, metal and acid. Okay, hold on. Metal and acid, if you put a chunk of metal in an acid, it'll react, but if you grind the metal into a powder, it'll react even more. And then how about when you cut up your vegetables so you can cook them? When you cut up your vegetables, you've increased their surface area and they're going to cook faster. And then how about this? If you put a teaspoon of sugar in water and stirred it, you've increased the surface area because that sugar is in crystals. What if you put a lollipop in water?
It's gonna like slowly dissolve.
Right. Yeah, it's going to slowly dissolve. Okay, and that would be true with a chunk of salt too, right? So the other thing to remember real quick is in this picture right here I showed you. See the leaves?
Yeah.
What chemical reaction takes place in leaves?
Photosynthesis.
Photosynthesis. Why are leaves broad and fat like that?
Because to produce food.
Yeah, if leaves were little, think about pine trees. Their leaves are like little needles, right? They have way less surface area than like an oak tree leaf. And that's because they have to stay green all year round to get enough food to survive. But those trees, the deciduous trees that drop their leaves, they only need a couple months out of the year of being green, right? Because they've got a nice big surface area and lots of photosynthesis. All right, temperature. Increased temperature is going to do what to the speed of your reaction? What do you think? You increase the temperature. What do you think, Emerson? It's going to increase it. Very good. And then Everly, what do you think is going to happen if you decrease the temperature? It's going to slow it down. Good job. All right. So temperature can affect reactions like that. All right. Somebody give me a real life example of temperature. What do you think, Annabelle?
Well, when like it's when like it's colder, like wounds may heal slower.
There are some chemical reactions that happen there. What do you think?
When you freeze a glow stick.
Oh, it glows for much longer, doesn't it? Yeah. All right, so food spoilage is a good example. Why do we use refrigerators? Because there are chemical reactions happening in your food all the time. Can you take a raw steak and keep it in the fridge forever? Will it still be good about a month from now? Oh, goodness, no, it'll be disgusting. If you leave it on the counter, is it going to go bad sooner or later than the one in the fridge? Much sooner. If you let it get warm, those chemical reactions are going to go faster and that food's going to spoil. So food boils faster at room temperature compared to a refrigerator, where low temperatures slow down the chemical reactions causing spoilage. Now, this is interesting. If you go to a buffet, the hot food is usually really hot. And that's because they need to keep it so hot that bacteria can't grow. But they can't keep it cold because it's supposed to be warm right? Like mac and cheese or something. But if there's a temperature range where it's safe because it's not going to grow any bacteria, but if it's warm and it's under that range, it will grow all kinds of things. And that's where people get sick at buffets sometimes. That and people put their own germs on everything.
Yeah, like it's because there are living organisms in your food that are slowly reproducing and taking over
Yep.
food, making it disgusting.
Yeah, there are living organisms everywhere that you can't see. All right, so dissolving salt in water. If you put salt in warm water, it's going to dissolve faster than if you put it in cold water. Who remembers the first lab where we separated sodium chloride and potassium chloride at different temperatures because of their solubility? Right, there we go. Okay, great example. Light sticks. You mentioned these glow sticks. If you put them in a fridge, they'll glow for much longer than if you leave them on the counter, take them out on a hot summer day. Cooking. Obviously cooking, food cooks faster at a higher temperature because the heat speeds up the chemical reactions that break down. Really what you're breaking down is proteins in your foods. And enzymes. All right, we're going to talk some more about enzymes, but enzymes are essential for many biological processes. They function optimally at specific temperatures, not too hot, not too cold. Enzymes are like Goldilocks. Okay, Goldilocks, remember? The bed was too soft, the bed was too cold, the porridge too hard, whatever. The porridge was too hot, porridge was too cold. You need it just right, right? Enzymes are that way. They need it just right. They're like Goldilocks. And battery performance. Batteries generally perform better at warmer temperatures. What happens to the Tesla drivers in Alaska or Canada? Sometimes their cars don't work because the battery's too cold and they won't function. Yep. All right. So also concentration. So we talked about concentration. The amount of a substance in a given what?
Volume.
Yeah, hands up, Emerson. Volume. There you go. Increased concentration is going to do what to a reaction? What do we think, Emerson? It's going to speed it up. And then Everly, what's going to happen if you decrease that concentration? It's going to slow it down, right? Okay. So, whoops, sorry. So why? Why does this happen? It's because when you have more of a substance in a given volume, you're going to have more collisions. Those particles are running into each other and bumping into each other more often, which means you're more likely to react. If there's only a few of you, you're not going to bump in. So think about it like friends. If you go to a party with 2 people and you're hoping to make a new friend, chances are it's going to be hard with only 2 people. But if there are 50 people at a party, there may be another person that you bump into that you can get along with, right? So that's kind of how it works.
It's like when you have like a closet and there's only one of you, like a big closet and there's only one of you, you're not gonna bump into
Yeah, you're not going to bump into anybody else.
Like 50 people in that, you're
Right.
definitely gonna bump in.
Right.
That's how reactions.
So what are some real life examples of concentration? Can anybody think of one? Here's some. So wait, can you think of one? That's okay. So acid and metal, again, we talked about this. If you drop a zinc granule into concentrated hydrochloric acid, it's going to react faster than if you have a diluted or less concentrated hydrochloric acid. Effervescent tablets. Again, this is Alka-Seltzer, right? Same idea. Little fizzy tablets. When you drop an Alka-Seltzer into water, the reaction is faster with a higher concentration of water because there's more collision. So you need more water for it to fizz faster. Combustion. Okay, this one's important. Combustion, fire, right? You have to have oxygen to have fire. Fire like eats oxygen, basically. It feeds on oxygen. It's necessary. So if you have more oxygen in an environment, you're more likely to have a bigger, hotter, faster, more damaging fire. So if you have somebody in your home, for example, who has an oxygen tank, you know, you've seen like sometimes people, like older people or handicapped people have a little tank and they wear like a little hose around their nose to get extra oxygen. You're supposed to put a big sign on your front door that says oxygen in use. And the reason for that is not so your neighbor knows. It's so if the firefighters come, they know something might explode, because if that oxygen tank, if fire gets to it, it's going to go really fast. It's a big deal. I made a friend of mine do that because my brother-in-law is a firefighter and she didn't have the sign up and her kid had oxygen. I was like, you got to put it up. You got to. I don't care if it looks tacky on your front door. Somebody's going to die. You know, if you have a fire, that would be bad. So in labs, we will very often adjust the concentration of reactants so that we can get to our products faster. All right, catalysts and inhibitors. Here's the big stuff. Catalysts and inhibitors. What do catalysts do to a reaction rate? Catalyst. What's it do? What's it do?
It increases the reaction rate. by
Yes.
lowering the activation.
Yes, it increases. What do inhibitors do?
But
Annabelle,
it's a substance used to decrease the rate.
decrease the reaction rate. That's right. And biological catalysts, those that are in your body and in the bodies of living things, are called what? These are called enzymes.
Oh,
So enzymes, we have all kinds of enzymes everywhere. So let's think for a minute. What are some examples of catalyst inhibitors? Can you think of any? These are a little harder to think of. Examples of catalysts and inhibitors. These are a little harder to think of. Catalysts or inhibitors. So catalysts, biological catalysts or enzymes. A good example is amylase and lactase. Amylase breaks down starch. And amylase, do you know where you find amylase in your body? In your mouth, in your saliva. They break down starches. You put bread in your mouth and you don't chew it, you just let a chunk of bread sit in your mouth, is it going to turn to mush? Yeah, it doesn't stay bread for long, right? It turns to like mush. It's because you have an enzyme in your saliva that's breaking down the carbohydrates and the starch. Okay. And then lactase breaks down a particular sugar called lactose that you can find in milk.
Yeah.
And then pepsin,
Yeah, like some people are
lactose intolerant.
Yeah, like when I was a baby, I was actually allergic to milk.
Yep. So lactose intolerant people they don't produce enough of the enzyme lactase, so they can't break down that sugar. And then pepsin, are you? Well, there you go. Well, you don't produce enough lactase. That's your deal. But you can take those tablets, Lactaid. Have you ever taken Lactaid tablets? They add some of that enzyme to what you're eating, and sometimes they can make it work for you. And then pepsin breaks down proteins. And then there are industrial catalysts that aren't enzymes. They're not biological. And they're things like platinum. Where's platinum? Here's platinum, right here. It's a transition metal, right? Platinum is in catalytic converters in cars. And it goes through a reaction where it helps break down some of the waste produced by the vehicle, the pollutant waste. And this is why people steal them. Platinum is very expensive. Like my rings are platinum. They use platinum in jewelry. It's very expensive. So because of that, people steal catalytic converters because they're worth a lot of money.
Aren't enzymes also catalysts?
Enzymes are catalysts, but they're biological catalysts. And then you have industrial ones too. Annabelle?
I just want to point out I'm not lactose
Oh.
or anything anymore.
Okay, well, that's good. All right, so then you have inhibitors. Okay, so biological inhibitors, medical inhibitors. So medical inhibitors, a great example is penicillin. If you've ever had like amoxicillin or anything like that, it's a type of penicillin. It's an antibiotic. And what it does is it blocks bacterial cell wall synthesis. So it makes certain bacteria, it makes it so they can't continue to live and thrive. So if you have a sickness or something, a particular bacterial infection, sometimes you might get an antibiotic for it. And penicillin is an inhibitor. And they use protease inhibitors for other, like HIV, people that have HIV, they'll use it to treat that, which is another an immune system disorder that you can catch, and then you have it forever. Some food related ones, preservatives that slow bacterial growth. You ever read like a processed food, like a Little Debbie snack cake or whatever, Twinkie, you ever read the ingredients? There's stuff in there, you're like, what is this? And it's stuff that keeps it from growing bacteria. It's an inhibitor, and they put it in the food. That's why you can have a Twinkie in its wrapper, not in the fridge, on the shelf for like months, and it's still fine. Kind of weird. All right, so let's watch a video on catalysts and inhibitors, okay? And I know there will probably be commercials this week, and hopefully they will end next week because I'm so tired of them.
Trump is elected.
Yeah, there it is again.
Abortion ban.
Yeah, that's the last thing I needed in class. Come on. All right, here we go.
Welcome to Moon Math and Science and the difference between a catalyst and an inhibitor. Chemical reactions need a certain amount of energy in order to happen. If they don't have it, the reaction probably can't happen. A catalyst is a substance that speeds up chemical reactions without being consumed. Sometimes a catalyst will lower the amount of energy required for a chemical reaction. Other times, it may change the path of the reaction, which speeds it up. Catalysts are found in the human body. Enzymes in your body act as catalysts to help with many chemical reactions that are required. Digestive enzymes are used in digestion to break down food. These enzymes are made of proteins. Your saliva contains amylase that breaks down starches. Lipase in your pancreas breaks down lipids when it's released into your small intestines. An inhibitor works in exactly the opposite way as a catalyst. Inhibitors slow the rate of reaction without being consumed. Sometimes they even stop the reaction completely. Some enzymes in your body are inhibitors. Many poisons produced by animals or plants are enzyme inhibitors that block the activity of crucial enzymes in prey and predators. Catalyst inhibitors do not change the amount of product produced, they just change the rate of reaction. Thanks for watching, and remember, kindness multiplies.
So change the rate of the reaction. So now we're going to look specifically at enzymes, and it's Amoeba Sisters. I love Amoeba Sisters. You could watch Amoeba Sisters all day. They're great. So this is going to show you specifically how enzymes work. So we'll talk about this more next year in biology, but it's like a lock and key. And there's other things in your body that work this way too, like antibodies and antigens work the same way, like a lock and key, but you'll see how this works. And this is great animation.
Odd to have a favorite protein? Well, I don't think so. Probably because my favorite protein happens to remind me of one of my favorite childhood games, Pac-Man. If you haven't played Pac-Man before, then chances are we're much, much older than you. But now you can play it on Google. Just Google Pac-Man. It's a Google Doodle. Anyway, I digress. But see, in Pac-Man, you have this little character. It goes around, finds these pebbles, and the pebbles fit right into it. Well, a lot of illustrations that you will find of enzymes, they happen to look, at least us, a lot like Pac-Man. I remember P for Pac-Man and P for protein. Most enzymes are proteins. Now, in the game, we mentioned there are these little pebbles that Pac-Man goes after. Well, enzymes have a specifically shaped area called an active site, where items can bind. The items are called substrates. It's very specific binding because the active site is specifically shaped for the substrate that binds there. Very specific. So what happens when a substrate binds an enzyme? Well, usually the substrate is held there with some weak bonds because it's not going to stay there forever. And something called induced fit will happen, which means the active site can change its shape even more to bind that substrate, like an enzyme substrate hug. The enzyme can either build up or break down the substrates that specifically bind to it, and we call the resulting item the product. An enzyme has the ability to really speed up reactions. Reactions that technically could happen on their own, but with the help of enzymes, they can be sped up to make processes effective for life. Let me give you a great real-life example. The enzyme lactase. Another really cool thing about enzymes is that they often end in ASE, like lactase. Many sugars, on the other hand, end in OSE, and lactose is an example of a sugar. Lactose is a disaccharide, meaning it contains two sugar molecules bound together. We don't actually digest it so well in that form. It's big. The enzyme lactase has the ability to break lactose down into smaller parts that our body can digest. And this is a lot better option than waiting for a chemical reaction with lactose to happen spontaneously. Now, with the lactase enzyme, lactose can be broken down quickly and digested. Now, there are some people that do not produce enough lactase. They can be what we call lactose intolerant, which means that if they consume foods that have lactose, such as milk, it can make them sick. They can't break the lactose down efficiently without lactase. In that example, one thing to point out, lactase, the enzyme, can break down a lot of lactose, the substrate. The lactase doesn't get used up in the reaction. It's still there. We call enzymes a catalyst because they can be used over and over and over and over in the reaction. By the way, your digestive system uses all kinds of enzymes. You have lipase, and that breaks down lipids, which are fats. You have amylase, which breaks down starch. You have protease, which breaks down proteins. So as you can see, the digestive system is very involved with enzymes. Another thing to point out is that enzymes don't always work alone. Sometimes they get some help. Some often underappreciated but essential little helpers are called cofactors and coenzymes. They may bind to the substrate or to the active site. They help the enzyme do its job of building up or breaking down substrates into products. Now, you didn't forget our Pac-Man analogy yet, right? In the game Pac-Man, there are these ghosts. And when they touch the Pac-Man, it makes this sound. It's like, no, no. And the Pac-Man shape gets all distorted in the process. So what does this have to do with enzymes? No, there aren't ghosts around, but enzymes do have certain ideal conditions that they like. For example, an enzyme that is in your stomach would have an ideal pH that is very acidic because the environment in your stomach is very acidic. Different enzymes have different ideal pH and temperature ranges. If an environment changes out of an enzyme's ideal pH or temperature range, then something that reminds me a lot of that horrible sound I'm trying to make can happen. The enzyme becomes denatured. That means its shape becomes distorted. It can no longer bind to its substrate. It can no longer work correctly. It is finished. Well, that's a dramatic end to enzymes. Keep in mind that if you have an interest in this topic, many medical researchers have a large focus on enzymes. Enzymes regulate a lot of the body processes, and many diseases can involve specific enzyme production, or the lack of it. Well, that's it for the Amoeba Sisters, and we remind you to stay curious.
So Amoeba Sisters are great. They're tons of fun. All right, so understanding main ideas. Let's look at your notes and see what we have here. All right. Use what you know about endothermic and exothermic reactions to explain the differences in the graphs above. Okay, what do you think, Yusuf? Eunice, what have you got? Wrong kid.
What do you call that? The endothermic reaction absorbs energy, where the exothermic reaction releases energy, and then you can see that the exothermic reaction has decreased energy. And from its reaction, like before, like one had the energy, it decreased energy, and then endothermic like gained energy.
Right. So basically, both reactions require that activation energy, right? To get started. But in the exothermic, I was reading it wrong. So this one right here, in the exothermic reaction, the products have less energy than the reactants. Do you see that the reactants are there, but the products are down here? So you found it? You still looking for it? It's okay. So you've got less energy in your products than you did in your reactants. And then your energy is released in that case, right? And then in your endothermic reaction, you've got more energy in the products than in the reaction. So in reactants. So here your energy is absorbed and here your energy is released. Okay. Why is the activation energy pictured as a hill? Do we know why it's a hill? Let's see if anybody else know. Annabelle, what do you?
Hold on.
Oh, she's got to find it real quick. Oh, she's looking.
Wait. So
There you go.
we haven't seen for chemical reaction.
Okay, yeah, so you've got activation energy pictured as a hill because the chemical reaction doesn't get started until the reactants have enough energy. They climb to the top of the hill and they get to a point at which bonds can be broken and then they roll down. So Your energy can build up, but your reaction is not gonna start till you get to the point where it can go down that hill, right? It's just like
a
rolling.
snowboard.
Yeah.
Like you're going up a mountain in a snowboard.
Yeah.
Like you lift the you do the chairlifting and
Yeah.
then you go down. You go to the top of the hill and then
Yes, you can think of it like skiing. So
ski.
say you wanna go skiing or snowboarding, all right? How are you gonna get to the top of the mountain? Well, you can walk, I wouldn't recommend it.
Chairlift.
Or you could take a chair lift, or you could drive, but all of those things take energy, right? You need energy to get up to the top of the mountain. You don't get there, you don't just appear there, it's not Harry Potter, you can't apparate unfortunately to the top of the mountain, right? So you need to use energy to get up, maybe you take the chair lift and it uses energy and gets you to the top of the hill, right? But you don't start skiing or snowboarding until you're at the top, because that's when you can go down. That's when your reaction can take place, right? Okay, so explain how adding heat to these reactions shown in the diagrams would change the rate of the chemical reactions. And then name 2 other ways to change the rate. What do you have, Annabelle?
Adding heat adds energy, concentration, and increasing the surface area.
Yes. Adding heat adds energy, very good. And concentration makes it more likely that collisions will happen. That's a great answer. So adding heat to a reaction supplies the reactant particles with more energy. Reaction rate can also be increased by increasing surface area, concentration, or adding a catalyst. Very good. Very good. Okay, so did everybody watch the balancing equations with marshmallows last week?
Marsh.
Did you watch the video, the lab,
Oh yeah.
where you
I
used the
saw that,
marshmallows?
The thing where you say metals, non-metals, hydrogen,
Yes.
and oxygen. So I've got one thing. Metals, non-metals.
Hydrogen and oxygen. So here's what we're gonna do.
It's like King Henry died.
It's kind of like that. So everybody's assignment for lab last week was to come up with a mnemonic device that you can use to help you remember in what order you balance your atoms. So it was metals, non-metals, hydrogen, and oxygen. So does anybody have theirs? I want you to turn them in, but I'd love you to share them too. What have you got, Emerson? What is it? Miss Nora has olives. That's a great one. What do you have?
My neighbor hates oatmeal.
My neighbor hates oatmeal. That's really good. I like that one. What do you have? You have one, Yusuf?
Yeah, I have one. Moms never hate oxygen.
Moms never hate oxygen. Well, that's good. I hope not. Everly, what do you have? My neighbor hates olives. You guys like olives or hate olives? Because you both put olives in your answers. Miss Nora has olives and my neighbor hates olives. Lucy, what did you come up with? Metals, non-metals, hydrogen, oxygen.
I think I said moms never hate olives or something.
Yeah, you can do that. Do you remember?
Come up with it.
Oh, okay, so you need to do that.
Watch the video.
Okay, so here's what we're gonna do right now. We're gonna take a minute and I wanna make sure everybody writes down, okay, everybody writes down their mnemonic on a piece of paper to turn in. But since we have a few minutes, we have about 5-10 minutes. I'm gonna give you your marshmallows now and let you guys practice for a few minutes. You're gonna wanna do it like, I'm gonna give you a piece of paper. You can do it on a piece of paper. And then be sure you hand in whatever you've written. Hold on, let me grab. What we'll do is we'll put the video on. So I have counted out, there are like 12 of each color in here. Okay, so if you want to eat them, you can eat them after you take them home, but you're going to want to practice with them today. And be sure you keep them with your stuff because keep them with your stuff because you're going to practice again after lab. So I'm going to end this, or actually no, I'll keep it up, but I got to change the Oh, I forgot to grab you paper. Let me grab you each.
Donuts.
Oh, we can in a bit. Sorry.
Donuts are the pink ones. The pink ones look like strawberry flavored.
He just wanted chocolate all like that.
Want to eat them, but we have to use
So what you're gonna do is you're gonna watch at least one of these and you're gonna use the marshmallows to do your balancing, okay? So you're gonna watch the screen and copy it, and then be sure that you take your piece of paper that you've written your memory device on and be sure that you turn that in, right? Okay, so let's go here. Let me pull up my video. All right. And then here we go. Pause it for a minute. And then let me swap this screen. Okay. Let me swap my screen real quick. Whoopsie.
Mr. Ron was talking about meeting Eddie Murphy.
I don't know what that is. All right. So we're just going to take a few minutes. And we'll start with this one. So you may have done, you may have done this already or practiced it already. And it's okay if you did. But we're going to do it again because you can't ever have enough practice with this. Come on, do your thing. Share that screen. Okay, maybe not. All right, I'll just stop it. I'll stop the Zoom.